Hi, and welcome to Logarithmic Differentiation. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at the Doña Ana Community College. I almost forgot where I worked. Can you believe that? This is a calculus lecture, Math 1411 at UTEP, Math 191 at DACC. Chapter 5, Logarithmic Exponential and Other Transcendental Functions, comes to us from Larson's 11th edition calculus text. Section 5.1 is the natural logarithmic function differentiation, but this is part 2 of that lecture, logarithmic differentiation in particular. So, logarithmic differentiation is a nice little trick to handle otherwise difficult derivatives. Do you have a whole bunch of product, quotient, and chain rule going on at once? Are you thinking maybe I'll just skip that problem because how much is this homework problem worth anyway? The logarithmic differentiation process allows you to handle those hard ones that you just don't have the time or energy for. So our steps will be to take the natural log of both sides of our equation. We'll simplify the right-hand side using logarithmic rules. Then we'll use implicit differentiation and finally solve for dy dx. Use logarithmic differentiation to find dy dx if y equals x times the square root of x squared plus 1 for x values that are positive. Notice we would have a product rule, and within our product rule we'd have a chain rule. Is it hard? No. But if we can do it quicker and easier, do you want to? Absolutely. So we'll take the natural log of both sides. That's the natural log of y equals the natural log of our product. We're going to use log properties to expand the right-hand side. So the natural log of a product is the sum of the natural logs, and the exponent, the square root of x, an exponent of 1/2, not square root of x, the square root, which is an exponent of 1/2, can be moved down in front. Remember, if you need a review of logarithmic properties, you should check out my pre-calculus lectures marked by 1508 and somewhere in chapter 3. Now that I have everything taken apart and everything as small as possible, I could use implicit differentiation. The derivative of the natural log of y is 1 over y dy dx. The derivative of natural log of x is 1 over x. Leave the 1/2. The derivative of the natural log of x squared plus 1 is derivative of the inside divided by the inside. But we're not finished yet. When we have 1 over y dy dx, we want to solve for dy dx. So here, I can simplify my 2's. 1 over y dy dx equals 1 over x plus 1 over x squared plus 1. Multiply both sides by y. But what is y? We know what y is. Y is our original product, x times the square root of x squared plus 1. And I can distribute. My x's cancel, I'm left with the radical, plus, not much to do here, so I just write it all together as a rational expression. This is my derivative. You would get the exact same thing if you would have used the product and chain rules, but it might not have simplified so well. Notice this is already a rationalized denominator, so that's kind of handy. If we use logarithmic differentiation on this product quotient couple of chain rule problems, nobody wants to do that. For x values greater than 2/3, we'll take the natural log of both sides, and that really just slap a ln in front of both sides. We use log properties to expand the right-hand side. So anything from the numerator will have a positive coefficient. Anything from the denominator will have a negative coefficient. The 2, the exponent, comes down in front as a coefficient, the 1/2 as a coefficient, the 2 as the exponent as a coefficient. Log properties, expanding. Now we can use implicit differentiation. The natural log of y has a derivative of 1 over y dy dx. 2 times the derivative of natural log of x is 2 over x. I have my 1/2. Derivative of the inside is 3 over the inside of 3x minus 2 minus 2. And you can write it out. Here's the coefficient. I put it in my numerator because the derivative of x plus 1 is 1 over the inside of x plus 1. So 2 times the 1 gives us our new numerator. Same thing we just had using implicit differentiation. Now we multiply both sides by y. And we know exactly what that is. And I can multiply times 2 over x. I can multiply here. Do I have to? No. This is a great answer. But if you wanted to know what it looks like simplified, you can follow the steps there. The thing I love about these video lectures is you can hit pause. Last example, using logarithmic differentiation to find dy dx when y is the square root of the quotient x squared minus 1 over x squared plus 1, and this is for x values greater than 1 only. We'll take the natural log of both sides, just slap an ln in front of it. Now, this square root goes over both pieces, so I'll have a coefficient of 1/2 on both of my natural logs. The natural log of a quotient is the difference of the natural logs, and I've expanded the right-hand side. Well, that wasn't very smart of me, was it? The right-hand side was natural log of y equals 1/2 the natural log of x squared minus 1 minus 1/2 natural log of x squared plus 1. Should have typed that on the new slide, that's my bad. My derivative, the derivative of the natural log of y is 1 over y dy dx. Leave the 1/2. The derivative of the natural log of x squared minus 1 is 2x over x squared minus 1, derivative of the inside divided by the inside, minus 1/2. Derivative of 2x, the derivative of x squared plus 1 is 2x over x squared plus 1. And I can simplify my 2's cancel in each of my quotients, multiplying on both sides by y, and I wrote it in the form of the square root of the quotient x squared minus 1 over x squared plus 1. Do I decide to multiply here? No. For many reasons, but mostly because this is calculus, and that's algebra, and I don't necessarily think the frustration of one should overshadow the ease of the other. So, if you get this far, you're doing fantastic. Logarithmic differentiation, excellent tool for taking apart difficult derivatives. That's it for now. I'm going to go adjust my mouth to make sure I can remember the words I need to say. Thanks for listening.